This is, in a sense, if I were going to relate it to the previous talk, we are looking at ways to characterize the shallow subsurface. And one of the ways one can do this also is with a drill by going down. And as you observe the drill's behavior under a given power level, you can characterize, and as you bring up samples, what you're actually drilling into at what depths down to a given level. Over the course of almost 20 years of developing planetary drills, myself and my co-authors here, along with the folks at Honeybee Robotics, have built up a substantial model for how drills behave for the sake of developing automation, as well as using a drill as a sort of an instrument to characterize what you're encountering as you go down. Now, Apollo brought up to a 2-meter drill. We're looking at similar magnitudes here. And so if the meta level here with respect to analog sites, it's not that a specific analog site, it's more that if you take this data on performance and the subsurface from several analog sites over years and years and build a good model with it, can you invert that model and not simply use it to control drills, but also use it as a inverting that model to try to tell you what it thinks you're seeing as you are drilling, to advise, say, a science team or astronauts if they were in that space. So next slide. And here's an example of several of these drills going all the way back to actually 2003 with the Dame drill, which isn't shown here. But these are some of Honeybee's drills. Icebreaker 1 went to Antarctica. We had several of these that have been tested in the Arctic at various locations, as well as lunar and Mars chamber tests. So next, please. And here is some listings going back at least to 2008. You'll note that actually several of these environments were, if you go back to the previous presentation by Pascal, were at Houghton Crater. And going from the Dame drill to Crux, Icebreaker 1, Leda, and then finally to Trident, although Trident has not been to a cold, icy environment yet. And I will mention as sort of an aside that since Trident is going on Prime 1 and on Viper in the next, twice to the lunar South Pole areas in the next year or so, talking with our friends at Honeybee, we both concluded it was probably a good idea to go to an analog site that has polymictic impact breccia and near surface ice layers, permafrost. And actually, since we have near surface ice and impactites, that this would be a good thing. We really ought to test as a risk reduction a Trident in that environment before we actually have these flight missions in 2 weeks. In fact, the stuff is actually on its way to Resolute as we speak. So we are following in the footsteps, and we will add another line across this hopefully in the next, say, month's time. Characterizing how Trident performed at Houghton Crater. Next. So, yes, it's all very interesting in terms of characterizing data coming back from a lunar drill and saying, how does this compare to what we saw at analog sites or in chamber tests? But more fundamentally, if we're trying to have enhanced situational awareness, we want an astronaut or a science team for a rover or a L-step mission to be able to make informed decision-making while we're doing drilling and sampling, being able to monitor the telemetry coming in and flagging when we think we are seeing, say, volatiles, or if we are getting stuck. And what does it mean if suddenly the rate of penetration goes to 0 and these other characteristics are happening? Are we seeing a hard layer? Are we seeing a change in material from what we had seen before? Have we hit a boulder down at 0.5 meter? So we might need to react to unexpected data or situations. Let's say if we have a Viper traverse and we hit something particularly interesting and it's identified in terms of volatiles or something unexpected, that might cause the science team at that point to wish to devote more time and attention, and they may need to replan or want to replan in that case. We have the luxury of doing that on the moon since since it's relatively close in light speed terms, you can have the possibility of near real-time ground processing of the data, whereas in, say, a Mars mission, it would have to be very self-contained, and only if you had crew members present on Mars could you do the same kind of processing. Otherwise, it would have to be very automated. Now, as a drill penetrates, it's going to encounter a range of densities and orientations, fracture toughness, and maybe volatile concentrations. And this telemetry can provide us with a quick look as it's happening into what the subsurface structure is, bulk properties, and constituents. Next. And I'll skim over this, that only to say that original 1980s expert systems in the oil and gas industry actually had sort of expert systems, very early AI, drilling advisor systems, which, so this is kind of amusing. It's like, you know, Back to the Future. Next slide, please. We have developed a notional mock-up console looking at the data coming in and mapping it to what we think we might see as we at a nominal console station during one of these. Next. Our automation architecture has evolved to track Trident. Our software has been tested in Chile and is implemented AI-wise in a planning and scheduling language called Plexel. I'm not going to give you the AI talk here, but splitting the top-level pattern matching and diagnostic reasoning agents off from limit checking is one way that we are substantially more sophisticated and capable than those 1980s expert systems. Next.
Just 1 minute, Brian.
Okay, I'm almost finished. We also have combined lab testing with simulants and volatiles, not just analog data. Here's an example of some recent ones that you'll hear something about probably from Carol, the next author coming up. Next one. And here is some analog data where we've actually identified constituents. This is one from Houghton Crater in 2016. Next. And from Chile with a Trident drill, but this is hot, dry stuff. And then the last, next one. So summary, large drilling data performance models exist that we have created from a decade or more of both lab simulant performance and analog field tests at multiple sites. These support near real-time interpretations of what happens when we're drilling, and that allows us to do near real-time, at least for lunar analysis, geotechnical analysis of what the layers and structure are by a science team or anyone observing. And this can improve our odds of both noticing gradients and anomalies and things like volatiles, identifying features while not getting the drill in trouble, safer drilling. So, thank you very much.